Hello everyone, I'm Mark Turgendi, the lead design engineer for Burt Process Equipment, and I wanted to welcome everyone this afternoon to Burt Process Equipment's educational webinar on pH system design. Just a few notes here as we get started. We will be posting a couple of poll questions throughout the broadcast if you guys have any interest in taking a look at those. Also, feel free to type any questions you would like into the webinar interface. We will try to answer most questions live today. But if we do run out of time, we will get back to everyone on all the questions that were asked. So sit back, relax, and I hope everybody enjoys this presentation. So first, what is a pH neutralization system? Well, pH neutralization system is one of the most important elements for treating wastewater in an industrial, laboratory, or an educational facility. And what we're going to really focus on today is going to be understanding how to do the process design for those systems, what are the two key elements that go into that. But in addition, we're going to look at some of the standard components that are involved in all these systems, a few of the different styles of systems that are available. We're going to walk through a few case studies here, going through how to size and design these systems, what kind of considerations are involved, how chemistry impacts the design, and then we'll look at a few standard models as well. So in doing pH system design, there are two primary factors that come into play. One is understanding the flow profile, both gravity and pumps, which is going to be transferring the wastewater to your system. And the wastewater, we're not looking at really wastewater that does not involve any kind of sanitary waste. We're talking about laboratory waste. We're talking about clean process waste, high purity water waste, chemical washdown, blowdown, a lot of different things that need to be looked at or treated depending upon the municipality you're in, all contribute to this flow profile. Equally as important to the system design as the volume is the nature of the waste. What is the actual chemistry that's going into your system or the actual waste product for which you are trying to treat? I want to start here a little at the beginning, talking about what pH is in general. And pH, simply put, is the chemistry of water. Anything that dissolves in water affects the pH in some way or another. And I have a few examples here you can see, some common household ingredients and how they have a direct impact on the pH of the liquid that they are dissolved in. Lemon juice down here on 1.5, orange juice at 3.5. You have a canned Coca-Cola or other soda, you're probably sitting around 4. Household bleach is pH 12. So even fairly benign things like this do have a fairly large impact on pH. And what's really important when designing a pH treatment system really isn't what that chemistry is necessarily, although there are a few different waste constituents that definitely do have an impact on pH. What is important is the logarithmic nature of pH. So the further you get away from neutral, you're increasing in relative strength by orders of 10, 10, 100, 1,000, etc. So if you're talking about something at pH 3 versus say pH 2, you're talking about a jump of basically like 90,000 in relative strength of pH, which is quite substantial in those cases. Before we get too into the system design, there are two macro system designs that have been around for quite some time. The first is what they refer to as a passive treatment system. This is what you may have heard or may have seen it referred to as like a limestone chip tank. They've been around, battery acid tanks. They've been around since about the 1950s. And using a passive medium, as I said, generally limestone in this case, the water's allowed to flow through. You have a contact time and pass out. This then allows for the dissolving of the passive medium, which then treats your waste stream. Passive systems, there's really only treat in one direction. They only can raise the pH, so you're only allowed to treat acidic waste. And those passive mediums are very weak relative to a lot of the different chemicals that come in. They generally only operate about 4 pH and up. So they don't see a lot of use anymore today. You do see them sometimes in smaller places, smaller, like for example, middle schools or high schools, places like that may still have a chemistry lab. They may throw a passive treatment system in. What we're going to focus on today is active systems. And active systems take real-time measurements of pH and then inject precision both acid and base chemistry into your waste stream to allow for complete treatment across the entire pH scale. Generally, waste streams tend to fall in kind of the 1 to 13 pH range. Once you get to that 0 or close to 0 or really like 14 pH, at that point you're talking about an actual measurable percentage by volume or by weight of actual chemistry in your system. You can treat that, but you begin to move the system away from the, wastewater more of a standard pH system design to more of a chemical reactor design at that point. And kind of just to point out, local municipalities do vary quite a bit in what they will accept for wastewater, but the most common kind of parameters you see, and this obviously does depend on the region you are in, somewhere between 5 to 10, 6 to 9, 5 to 11. So you generally get a little bit more on the basic side, but that's kind of the general range in which you fall in. So actually going back to our previous slide, if you had actually dumped bleach down the drain, you would actually be out of compliance in most states for pH adjustments. Among the various active systems, there are three primary types of wastewater treatment systems: the flow-through system, the batch treatment system, and the hybrid flow batch system. 90% of pH systems are what's referred to as a flow-through system. Waste enters into a treatment tank or series of tanks. It is treated and then allowed to flow out as a steady state. The benefit of flow-through systems is, as waste comes in, waste is then displaced and leaves, and you can put through a very high throughput for your system. And if you size your treatment tank or tanks properly, based on proper residence time, you will generally end up with a very functioning pH adjustment system. Batch systems, on the other hand, a volume's allowed to enter into your process. You shut off the influent, you treat that held volume. Once it's fully neutralized or treated, you then allow the waste to drain out of your system, and then you can fill your process up again. It gives you the advantage that no waste is going to leave your system that hasn't been treated. The downside is it really does reduce your throughput. There's a fill time, there's a treatment time, a verification time, and then either a pump down or a drain down time. So that whole process could take 45 minutes to an hour, and that's only for a single volume. So, for example, in the flow-through system, if you're going to run 20 gallons per minute, you could treat 1,200 gallons in that hour. If I had, say, a 200 or 300 gallon batch tank, I'd be treating 200 or 300 gallons in that same hour period. In a lot of industries, pharmaceuticals, semiconductors, even in manufacturing, they tend to have more extreme waste conditions than you would see in, say, like a laboratory environment or more like an academic environment. People often go what's referred to as a hybrid flow system. This offers both the advantages of a flow-through style system while still having the built-in ability to go into a batch mode temporarily, either within the treatment system itself or by using an equalization or not a specification tank. Waste flows through your system, and when you have those higher peaks, you can shut off your effluent and still allow your influent waste to come in, treat it for a longer period of time as you would in a batch situation, and then allow the flow to leave the system normally. So this is what you generally see a lot when you have high flow and more extreme waste conditions. Kind of regardless of the type of treatment design used, whether it be flow through, batch, or hybrid, all these systems have certain major components: treatment tanks, agitation, chemical injection controls, instrumentation, as well as effluent monitoring. You can see kind of some examples here on the screen of kind of a standard dual stage. This is a 4-stage system with containment. This is really more done for room as opposed to really generally the need to go into more of a 4-stage style system. The treatment tank is the heart of the pH treatment system. And again, regardless if it's a flow-through or a batch, there are certain commonalities. The treatment tank is designed with what's referred to as a CSTR, a continuously stirred tank reactor. In chemical engineering terms, what that means is this tank is agitated as either the volume is held in a batch style system or as flow is allowed to enter it in a flow through system. And you are mixing this into a well-mixed solution. So the pH and the chemical consistency of this tank is uniform throughout. That way, when you're doing pH adjustment, you're treating this volume. You're not actually treating the flow coming in and out of your system. And this is achieved by the rate of mixing and the residence time, which for most industries is 20 to 30 minutes. As for the materials, because you're dealing with a lot of corrosive chemicals, very often these systems are going to be polypropylene, polyethylene, possibly PVDF or Kynar, generally thermoplastic materials. In odd situations, you will see things like stainless steel or fiberglass as well. The rate of mixing is important in achieving that CSTR reaction because it's really the rate of mixing that creates that well-mixed solution. Looking at kind of the inside of a treatment vessel, waste comes into your system and then is directed down right into the mixer backwash here. This is your chemical injection ports up here, which also follow the inlet down. The reason to direct the waste to the bottom of the tank is to prevent what's referred to as short-circuiting, whereby your waste will enter the treatment tank and essentially go straight across right to your effluent. By driving the waste stream down into the mixer backwash with the reagent chemicals while you're adjusting, you end up with a very uniform mixture. The pumping rate, and obviously mixing, does vary depending upon incoming flow rates, tank size, volumes. There's kind of a general rule of thumb. You're generally looking at about 1.5 to 2 tank turnovers per minute as a pumping rate. What that means is if you have a 500-gallon tank, you generally need about 750 GPM to 1,000 GPM of mixing going on in your tank, which is considered moderate mixing for the most part. On very small tanks, people do use recirculation pumps for agitation. It's not as common on bigger tanks to utilize this or bigger systems as a mixing means, and that's because, as I just said, you need a really substantial pump and a lot of power and horsepower to really get that agitation going. Instead, on larger systems, recirculation pumps are utilized more as a carrier medium to allow for easier reagent injection. So an example I'm showing here, we have our chemical injection located here at the top, and then they basically have down pipes going in. You can kind of see in this picture as well. That just basically drips into the solution right into the mixer backwash. By utilizing a recirculation pump for chemical injection, you're now injecting into a pressurized line, and then that fluid is utilized as a carrier medium and educted into your mixer backwash, which gives you a much faster rate of injection. So that's generally where you would see recirculation pumps used, and that's done a lot on either much larger systems where ergonomics comes into play, and you don't want to be having injection going into a tank that could be 10 feet tall, or where you have a very strong waste stream. This will help speed up your reaction time within your system. Speaking of chemical injection, there are two common chemical reagents which are utilized in these systems. The sulfuric acid, generally in the 50% range. Some people do use 93%, 98%. And then sodium hydroxide, 20, which is generally utilized at 25%. The reason for the reduced level of caustic is not so much a chemical safety, but more of a concern of freezing. 50% caustic can turn into almost a jelly-like substance at about 55 degrees Fahrenheit. Reagents are stored 110% containment and obviously stored separated due to the reactivity between acids and bases should they mix in their reagent form. As for the actual chemical injection, because pH is logarithmic by nature, your reagent chemicals are orders of magnitude stronger than what your actual waste stream is. So if your waste stream is even pH 2 or pH 12 in that case, your sulfuric acid, your sodium hydroxide, they're going to be 9 million times basically, or 2 orders of magnitude stronger at that point than your actual stream. So you generally, when you use something like an electronic metering pump or some kind of a small peristaltic pump, or very slow, very precision injection, of your reagent chemicals. As for control, for the most part, pH systems rely on what's referred to as proportional control or temper proportional control, whereas you are scaling your chemical injection, both acid and caustic, to match the pH curve. So if you can see here the pH scale, excuse me, when you get further out in 0 to 14, to 1, 13, the difference in relative strength between your reagent chemistries and your waste stream is not that substantial. So you're going to run your chemical injection at relatively high speeds. As you start to get closer, 2 to 3, 10 to 11, you need to really scale down your chemical injection really to match the pH curve, 10, 100, and then probably 1,000 to 1 turn down as you basically approach 7. That's how most pH control is done. People don't tend to use titration control when looking at pH systems because titration really relies not just on pH, but also what the constituents are of the waste stream, what the relative alkalinity is, if there's any kind of organics, things that could impact to do a volumetric addition. This is what you're going to utilize when you have really a broad range of chemistry which could be entering into your system. One system which really ties into pH systems, although it's not directly a part of it, is equalization tanks. And for the most part, we've been talking about kind of the pH system, the tanks, mixers, the pH instrumentation. Equalization tanks are generally used to help size and/or control the pH adjustment going on within your actual system. And equalization tanks are storage vessels that go upstream of your system. And for the most part, what you're trying to equalize with these systems isn't really pH, it's actually the flow coming into your system. Really everything in the pH system from a sizing standpoint, tank volumes, which then affects the mixer rates, skid sizing, is all based on the amount of throughput you're trying to put into your system. It's much easier then to equalize flow than then put a very common flow profile through your system to allow for easier treatment. It also then gives you the ability to scale back to it should you need to in the event of an out-of-spec situation. Equalization tanks are not that good at equalizing the chemistry of your waste. The reason being is if you mix a pH 11 and a pH 2 waste stream together, you're more likely going to end up with a pH 2.1 waste stream. Again, because of the logarithmic nature of pH, self-neutralization by equalization is very hard or really impossible unless you have 2 waste streams of equal volume and equal pH, which is pretty rare in those cases. Equalization tanks become much more important when you're talking about process, pharmaceutical, or industrial clients, and they can see very, very large waste stream swings. For example, the dumping a process kettle, or other equipment is running, and they could be dumping something at 100, 200 gallons per minute, but for a very short amount of time. You don't want to be sizing your pH system for that very large volume. You want to collect it, equalize it, reduce the footprint cost of your system by then transferring that to your system at a much more controlled but consistent rate. Now that we've talked a little bit about some of the different components that go into these systems, when actually doing pH system design, you do need to look at, as I mentioned before, really 2 big parameters. One is the nature of the waste, and the other one obviously being establishing the flow profile. And the nature of the waste can sometimes be easy and sometimes be pretty hard to understand. Because it's not always evident, particularly if you're working on a project for a building, for example, if you're a design engineer that hasn't even been built yet, or you're working with a client, or you are a client in an industrial, and you're trying to design a system for a process you're still optimizing or that could change, it can get kind of hard to really understand what's coming into your system. There's a few guidelines to kind of think about, things that definitely come up in different industries, whether it be biology or pharmaceuticals. chemistry, clean room, animal handling, semiconductors. All those things tend to have certain waste characteristics that you might want to account for that could come up down the road. For example, in pharmaceuticals, you're going to see a lot of, for example, like CIP, which is called clean-in-place chemistry, potassium hydroxide, phosphoric acid. Semiconductors, you might see a lot of like high acids, things like hydrochloric acid, possibly HF, which may need to be accounted for, deionized water. If you're looking at an academic building, biology, you're going to see some acids, bases. You're probably going to potentially see some solids. If you have any kind of animal handling, chemistry, again, you're going to see. So there is a fair amount of diversity, things you can kind of plan for with these systems, but it is a little bit tricky, which is why you generally want to do, which is really where the idea of residence time comes from in these systems. Acid and base reactions are actually some of the fastest in chemistry. The reason you really account for that residence time is to actually account for a lot of that unknown going on in your system. One thing, though, I do want to note in particular is if you do have the presence of high purity water. High purity water, which is obviously which is made from either a WIFI process, RODI, or reverse osmosis deionization, which is referred to as high purity water, is very common in a lot of laboratories, college, industrial settings, pharmaceuticals, and now since it's a purified water source, it very often does get into pH adjustment systems. And one of the byproducts of creating high purity water is the removal of the alkalinity. And alkalinity is a measure of the buffering capability or the ability to neutralize acids and bases in solution. So what does that kind of mean in layman's terms? You have things in your water, you have hardness, you have chlorides, you have metals, you have colloidal matter. These are all things that are dissolved in the water that, we drink every day, that we have, that from a high purity standpoint, we obviously don't want in there. We want to be looking at things like resistivity, we want to like reduced TOCs, but these things also offer essentially a chemical sink when we're doing our wastewater treatment. So if we're putting our acids and bases in there, they're going to react with some of these other chemistries beyond just our waste constituents to allow for, a buffered wastewater treatment. When you have removed that as a function of high purity water, what really ends up happening, what you see here on the left-hand chart, as you kind of begin with a linear slope towards neutral, and basically what that is the pH scale 1, 7, and 14 versus treatment time. And as you begin to get closer to neutral, your reagents basically overreact with your waste stream. So it causes you to then jump substantially more than you should have in terms of pH adjustment. So you can go up from say 5 all the way up to 11 pH. Which will then activate your acid pump, and then you'll shoot all the way back down to 5, and you basically just keep oscillating back and forth, and this can go on for 24 hours until finally you end up basically stabilizing your pH. The stronger the high purity water, for example, in semiconductor industries, this may never really get back into a good treatment scheme at that point. So to accommodate that, a third reagent is added to these systems, and that's in the form of a buffer. The buffer typically being sodium bicarbonate, which allows for buffering in both the acid as well as the base direction. So you get that nice linear line that you're looking for as part of a pH adjustment. So I pulled the titration data here. This is actually a client, and I kind of wanted to walk through some things we talked about, the relative strength of pH, alkalinity, by showing some actual real data here, and how that kind of impacts when you're doing your system design. So what this chart is showing here is pH as is neutralized 0 to 14 on the left, and then the volume of reagent to the volume of waste being injected. And I'm not going to go into exactly what these chemistries are, but here, obviously, we have a very strong 13.5. This is actually potassium hydroxide. Down here, we have a 1.5 acid stream coming into our system, and then these sort of straight lines here. Not a lot of reagent injection. These are waste constituents that start low, 2.5, 4. This one up here, 11. that really don't take a lot of chemistry to move them. This one here is a very linear, nice, good slope. This is a well buffered, fairly normal waste volume. 11 goes straight down to 7 with fairly minimal, with fairly minimal amount of reagent injection. I want to talk a little bit about I do want to talk a little bit about these other two lines here. So this 1.5 acid stream, you can kind of see the points. I hope you guys can through the webinar. You have these are different titration points here, and then all of a sudden when I get to my pH 4, I go jump all the way up to pH 10, and then I continue on. This is a classic example of a low alkalinity waste. So instead of this nice, dots we get here, nice titration points, we go right to here, and then we shoot straight up. If I then proceeded to add acid to this, I would go straight back down and end up in a very similar place here. So this kind of highlights what alkalinity looks like when you have low alkalinity in a real situation. The pH 13 waste stream here, you can see it takes orders of magnitude more. The tree, again, being much stronger, this is really highlighting the strong nature of these, logarithmic nature of pH. When you're going way out here to basically an order of magnitude higher to actually get any kind of waste treatment. So it goes all the way out and then begins to follow a bit of a linear, but even this one here probably has a bit of low alkalinity because then you get some jumping going on around the neutral point. We do have a question here, and that does concern the alkalinity. Alkalinity is a bit of a tricky subject because it's not something that you really, it kind of gets a little bit into the chemistry here. And the question is, does buffering only happen near the midpoint pH or can it happen at a higher or lower one too? So buffering does not only happen at the midpoint pH. But for pH, from a pH adjustment standpoint, that's where we want to control the buffering if we need to, if we have a low alkalinity waste stream. There are buffers that work at really almost any pH, and kind of an interesting thing, buffers are actually utilized to calibrate pH instrumentation. They're generally a 3, 6, 9, 12 buffers, which are actually utilized when you're calibrating your pH probes for maintenance as part of a pH adjustment system. Because the reason why you see this kind of alkalinity pattern here, as you get closer to neutral, kind of to the midway pH, is because at that point your reagent chemistry is so much stronger than your waste stream. It gets very, very pronounced. But even here at the lower pHs, 3.5, 3, you start to see a very, very vertical peak. That's a sign of low alkalinity. Here you would see a much more linear peak. So you definitely have a buffering concern down here. It just doesn't quite impact your pH system until you get to that more more midpoint pH range. But buffering definitely is a concern. I didn't talk about it in this talk specifically, but I'll bring it up here real quick. There is a reverse problem that happens sometimes in pH systems where you have too much alkalinity. And this is a problem when you have boilers, you're cracking, you have large boiler waste streams where they're just doing cracking in there of the chemistries, or if you have things like glacial acetic acid or some very strong organics potentially in a pharmaceutical, you can end up with buffering. When you have, for example, when you're doing boiler cleaning, they tend to buffer way up here in the pH 13 range. So what happens in those situations, which is obviously shown on this chart here, is you would get a very linear curve because basically your chemistry is reacting with the buffers in that range, and then it would just drop like a rock because you don't actually have enough chemistry there that you're reacting. You're just reacting with buffers at that point. Glacial acetic acid tends to buffer in the lower, kind of pH 3 range. And again, you get instead of getting a nice linear curve, you're getting a very vertical curve, you get a very flat curve, and then you go straight up. That's what happens when you have too much alkalinity in your system. It's a little less common, but it does come up in different pH systems. So we do have another question here about the buffering and alkalinity. The question is, does sodium bicarbonate help with the purple line where it takes forever to reach the vertical part of the graph? So I'm not sure which the purple line is. I'm assuming it's this one here. The bicarbonate would not help you neutralize this. Bicarbonate itself can act as either an acid or a base, but it's a very weak acid or base. So it will act as a buffer, but it will also act as an acid and a base, but it will not have enough. It won't have enough potency to really impact this treatment or move this so it goes back over here. Generally speaking, if you have a waste stream like this one present, you might want to consider a couple different options. One, this might be an indication that this is a waste stream that can be taken out of your system, that you might want to look at like a batch style system, where you want to be able to treat this for a longer period of time. You might also want to go to a stronger reagent for those systems, whereby you could then, for example, in this case, we know it's pH 13.5. We might want to use a 98% sulfuric for higher molarity as opposed to our base in those cases, as opposed to the 50% in those cases. But no, the alkalinity treatment will not help a strong waste stream like the dark purple line. So, kind of moving away from the nature of waste for a second, I kind of want to talk about the other portion of this, which is obviously when we talk about flow profile. And we talked a little bit about flow, equalization, how gravity comes back into our system. And sometimes gravity is simply just not your friend when it comes to flow. This is very common if you have your pH system in a mechanical space on the first floor of a building or first floor of an industrial complex. And you also have laboratories in that area that you need to actually put to your waste stream. It's tough. It's doable to put a pH system in a pit or some kind of a lower level than that, but oftentimes it's just easier to put in a lift station or a transfer station in those cases, like something like the one shown here. And there are a couple of different types of lift stations. I'm not going to spend a ton of time reviewing this today. There are simplex lift stations. These tend to be used more for under the sink kind of applications. And then you have, generally, due to their lack of redundancy, they're utilized systems that don't run very much, a single lab sink, very common in retrofits that you want to transfer to your waste application by putting in, say, a new clean room lab. I could put a single simplex in there just to pump over into a current lift station. Or if I have a non-critical process, which doesn't mind being down for long periods of time, for example, for maintenance. And then duplex lift stations, obviously this is for an entire lab. If you have, for example, a first floor situation like I was kind of before, and you have a pH system on that level, you can bring all of your waste stream to one duplex system and then pump it into your pH adjustment system from there. So when talking about flow, one of the first things to do is just how what's referred to as the flow profile. So when you're looking at lab sinks, cup sinks, fume hood, you can make some assumptions on those based on charts like this. One lab sink is 1 gallon per minute, one cup sink's half, fume hoods, and then apply a diversity factor across those systems. So generally a good diversity factor is 20 to 30. I generally lean a little lower depending on what your application is. If it's a university, for example, it's more of a industrial lab, probably a bit of a higher diversity. And then you have a lift station, those you have to size differently because you have to size those based on the maximum flow, unlike in your drainage situation. So looking at one example here, we have 80 lab sinks, 5 glass washers, and 10 autoclaves in our fixture count profile. And we're going to skip these, I apologize, slight error of a repeat. So for the from a pump standpoint, we have 20 lab sinks and 2 glass washers. We calculate that as 1 GPM for 20 sinks is 20 GPM, 2 cage washers, 16 GPM, 36 GPM total. When you're talking about a lift station-based flow, you cannot take a diversity. That only applies when you're doing gravity-based flow. A pump system has to be sized for the maximum flow that could come to it. So lift station sizing, generally you want to go 10% over, because you always want to assume that you're going to be pumping down your lift station. So if you require flow rate of 36, you generally want to run it at 40 GPM to get a hot, that way you're always pumping down your lift station. And you generally size it for a run time of 3 to 5 minutes. Generally, most pumps you don't want to run more than 12 times an hour. But obviously, there's things that come into play, how much room you have for the system. Most lift stations, they try to make the tanks as small as possible for real estate purposes as well. So for the gravity flow, you have 60 sinks, 3 glass washers, and 10 autoclaves. This one we can take the diversity. So we look at this. We have 60 GPM from our sinks, 60 lab sinks times 1 GPM. Our fixture flow, 60 GPM times a 20% diversity is 12 GPM. Again, assuming a reduction in cage washers, 16, 5 autoclaves, 10, we have a total flow of 38 GPM. So we end up with an estimated flow less than we would for the reduced sink counts, for the reduced fixture counts from our pump system. But however, we always know that the pump will activate at that 40 GPM, so we have to account for that in our pH design. This is what we're going to, this we have to take a diversity. This is what you're generally going to see coming into your system. So then our total flow is 78 gallons per minute. So 40 GPM pump, that'll cycle obviously, but if it comes in contact, but it comes at the same time as our gravity flow, we will have a total flow of 78 gallons per minute. When sizing a pH system, you do have to size it based on the maximum flow rate coming into your system. It will be that time when you say you sized it for an average flow. The average flow in this case would be 39 gallons per minute. If you did see a 78 GPM, you would run the risk of end up going out of spec with your system, and obviously going out of spec entails a lot from a fine standpoint. Reviewing the waste profile would also come into play in these cases. So, I mean, if this was, say, a standard, maybe collegiate lab style billing, you're probably looking at pH 3 to 11. And then special waste considerations. If you did have high purity water, you'd have to have your bicarbonate addition. So, looking at a fairly standard pH system design here, 78 GPM, 20-minute residence time, 1,560 gallon total volumes. We have 2 800-gallon treatment tanks. From a graphic standpoint here, this is our 2 treatment tanks. This is our reagent injection. That's our bicarbonate injection, P and ID. This is our acid and base, bicarbonate, and our 2 treatment tanks. So that's how you would, in a relatively simple sense, size a system based on a not particularly complicated waste profile, but looking at it more from a flow profile perspective. I'm going to switch now to talk a little bit about a couple of standard system designs. And these systems, what Burt Process has done is we have kind of taken some of this design work out, where we have kind of set these up based on the different flows the different flow rates, looking at some different waste profiles, and then also kind of have standard models here conducive to certain flow styles that have already generated drawings, specifications, utilities for end users and engineers to review and allow for a simpler, faster system implementation. The first one is what we refer to as our PHX style system. And PHX systems, they're designed for small applications, 7 GPM up to 33 GPM. We call them the PHX 100, 200, 300, 400, and 500 respectively. They're a fully engineered unit, single stage. They're designed for more standard waste streams, really your kind of 3 to 11, 2.5 to 11.5 pH ranges. They're nice in that they're very small. So, for example, if you have a very small lab that you're working on or small facility, the PHX 100 is just 2 feet by basically 4 feet by 5'9". It can be plugged into a 120 volt wall outlet as a fully engineered system. The larger unit, 6'4" by 4" by 5'9", isn't much bigger than a standard office desk at that point. And these have built-in 20 or 30 gallon reagent volumes, disconnect, control consoles, and can have an effluent monitoring package easily added into them. So these are really good when you're looking at fairly simple waste streams, and it comes with a pre-engineered package. And they're even kind of conducive to different flow profiles. So if you have a PHX 100, you have, say, 20 lab sinks, 200, 21 to 45, even PHX 590 to 110 is kind of what you would almost assume, for even a larger collegiate lab building could be handled by one of these standard units. And this is a PHX. This is obviously a little bit of a base plate here, but you have your reagent tanks. So you have your reagent tanks, control console, metering pumps, and the back of the system is your treatment vessel. Highlighting how those numbers are generated. If you have a 75 sink, this is, say, a 7th-floor lab building. Looking at our flow profile, very similar to what we had just talked about. 75 GPM leaves a 30% diversity. Some municipalities actually require different diversities by code. Just one example, for example, like New York City, they want a 30% diversity. They actually do specify. A lot of them do not. They're one of the ones that do. That's why I say 20 to 30% diversity is fairly common. So at 75 GPM, that's 30% diversity. We end up with 22.5 GPM. Again, looking at our pH range, this is a basic 7-story lab. PHXs tend to operate really, I said, that kind of 2 to 12 range. 4 away from neutral. This is kind of a perfect PHX 400 with a little bit higher diversity. You can probably use a little bit of a reduced residence time. Again, if I said 20% diversity, I know it's just a 20-minute residence time in this case for a 337.5 gallon, which is a 400 gallon ACS system. Excuse me. From a PNID standpoint, this is your treatment tank. You have your agitator, chemical injections, vents. Vents are required for all pH adjustment systems. And it is best to vent them out of the room. You are putting a waste stream into a treatment tank that will then be held, and depending on what comes in there, what the frequency of dumps coming into your system is, you can definitely end up with some fumes, really more of a biologics fumes, or as opposed to a chemical fume coming out of your systems. I would definitely advise venting these tanks out of the room if at all possible, and that's really regardless of any pH system. This is what a PHX looks like from a drawing standpoint. This is your top view. You have your access manways. That's your downpipe, chemical injections, like a standard pH system, vent connection, mixer. From the front, this is your control console. Here, you have your metering pumps, low level switches. Behind this panel here is your reagent tanks, which are 110% double contained. Same thing for your caustic side here. Looking at the inside, again, this is your reagent injections going in, pH probe, there's your agitator, and there's your effluents, as well as your power disconnect switch. So when you're moving into the larger or more of the industrialized systems, this is where Burt Process equipment offers its ACS or assured compliance system. And the assured compliance system is an integral hybrid system. As we had talked about hybrid systems earlier, this is a system that incorporates a flow-through system, but also has an integral batch compartment associated with it. In a standard ACS system, that batch is actually built into the base treatment tank. That's achieved by having a built-in freeboard above your standard effluent U-trap, highlighted in the picture here. This is your standard effluent point, and this is your ACS point. So if you had to, you can go into a batch mode where this additional tank volume could fill up for treatment. That's standard on an ACS style system. When more than that volume is required, and that volume is usually 3 to 5 minutes of additional residence time, which doesn't seem like a lot, but it really is a 20% increase. That can be enough to get you into compliance. If you do want to go higher, this can also be changed to be recirculated back to an equalization tank or an out-of-spec tank. This is very commonly used in industry applications, pharmaceutical semiconductors. They're skid mountables. A single skid up to about 300 gallons per minute. And it can be done in multi-skid modules up to about 500 gallons per minute. These incorporate a lot of the features. The recirculation pump, as I mentioned before, is on these systems. You can draw out and go back into your tank as an eductor for your reagent injection. These can be single or dual stage as well. You don't see a lot of dual stage systems for these because you do end up with a much higher reaction time based on the way you're putting your reagents back in with the recirculation pump. Built-in lift stations, instantaneous flow, temperature control and monitoring is available with these systems. Redundant pH probes. The pH probe, redundancy in pH probes is generally done with 3 pH probes as opposed to 2. The ability to use 3 allows you to have a reference probe to compare the other 2 probes to, so you can end up with a comparison. So if you have one probe which is reading 5, one probe is reading 9, then your comparison probe is reading, say, 9, you know obviously which probe is bad, as opposed to having some different probes available. As well as these come standard with a full PLC system, which can then talk back net or Ethernet into a building BAS system or a SCADA-based interface as well. Standard models for these range from 50 GPM up to 150 GPM, and they all standard 20 or 30 amp 460 volt 3-phase. And as a tank capacity, these things do get pretty big. An ACS at 150 is going to have a 3,750 gallon tank to achieve that high level of resonance and still have that built-in freeboard capacity for these systems. Graphically speaking, this is your reagent station here, recirculation pump and the effluent U-trap, obviously much larger vent due to the flow capacity, mixers and manways. The side view here, control panel, and then the front view here, you can see that's where your pH probe is located. Generally, these use extraction style pH probes as opposed to insertion style. The benefit being is this allows for much easier ergonomic removal, as I mentioned earlier, and it also allows you to, by looking at the pH probe in the recirculation line right next to where your reagents are going in, you're getting a very instantaneous reading for how your treatment is progressing into your system. Looking at a P&ID here, waste comes in. Sometimes you have a small equalization area in these treatment tanks separated by an over-under baffle. That's not always a requirement. Some people like it as a feature. This goes into your primary treatment tank. Again, this can be a 2-stage system here where you have your double U-trap. This is your standard effluent. When the waste in this treatment tank is not in specification, and again, this is still a CSDR reactor, this valve will close and you'll be able to rise in water level to a higher level. This high level switch is set at that point, so you'll know from an alarm standpoint when you do get to the high level overflow as part of your ACS system. Your circulation loop, you have your pH probes, flow switch to protect. You never want to be injecting chemistry if you don't actually have flow in your system, which is why the flow switch is here. Then your acid and base reagents, which come back into your educting into your mixer backwash here. There are a lot of options that go into systems: 2-stage, multi-equalization tanks, effluent transfer, but this is your basic ECS P&ID. Looking at one example here for an ACS style system. This is an ACS 100 with built-in heat exchange control. One of the questions that does come up quite a bit is temperature and what temperature you can discharge from a building. And as a general rule of thumb, it's 140 degrees. Although in some areas also it's actually 104 degrees. And that does depend on the local codes. And I mean, you're talking about things like steam condensate. If you have things like that getting dumped down the drain, you're going to be using hot water sanitization for your system or cleaning chemicals. Those may be coming in 185 degrees up to 200 degrees. You do need to control the temperature as part of that, as part of your wastewater treatment system. Generally, the temperature control is on the influent side of your pH system because you don't want to be designing your pH system for high temperatures. You really want to be designing it for the corrosion resistance. So 3D models for these systems are also available online. So the ACS 100, as I mentioned, this is with a heat exchanger, continuous flow, secondary heat exchanger skid, PLC control, effluent flow, pH, and temperature monitoring. And again, we still apply the same basic steps. You want to apply you want to develop your flow profile for these systems like we've done previously today. 60 lab sinks, 6 process kettles. These work in a dump during a cleaning process, cage washers, and autoclaves. So again, looking at our example here, 1 GPM times 60 laps, 60 gallons per minute, 20% diversity. We end up with 12 GPM, 16 GPM per cage, 10, and then looking at 2 kettle dumps at 60 gallons per minute, we end up with a 98 GPM flow rate coming into our system. This is a pharmaceutical application. We're going to have a lot of those clean-in-place chemistries, phosphoric acid down here on pH 1.5, potassium hydroxide at pH 13.5, citric acid at pH right around 3 to 4. So we do have a very strong acid stream in this case. We're going to be looking at probably using stronger reagent chemistry for treatment, as well as having that ACS features. And we do see this potassium hydroxide dump, we will increase our residence time for better treatment. 98 GPM trace treating chemicals. This is definitely a hybrid style system, as we've already talked about. And 98 GPM at 25 minutes, 2,450 gallon treatment volume. Beyond just the sort of standard and looking through a couple of different case studies, there is a lot of different, more custom-based systems that still utilize a lot of the same technologies we've talked about today. One of the systems here on the left is actually a pH system designed to go outside. It's not a common application, but it's becoming more common today for people to want to move these systems, particularly if they have modular building design going on, to move pH adjustment systems outside. This particular case, you have a panel air conditioner, you have built-in double containment, hot boxes over your metering pumps. This is actually probably the less common way to do it today. What you're seeing a lot more is actually containerizing these systems in small buildings as a module as opposed to a skid, bringing them to the site, and then they're pre-tested, they're pre-wired, and they can just bring power, bring your effluent, and you're good to go. Second one here is just a large dual-stage system. It has an integral effluent lift station associated with it. This is what you might see in maybe a big college, for example. It's going to be located inside like a sub-basement for one of those applications. Third one here, very similar single-stage systems. And then finally, you can get into more process-based systems. This is actually a hazardous location pH adjustment system, whereby you have your equalization tank that then feeds into a treatment vessel. They were actually treating very strong waste here with hydrochloric acid. This one's also located outside, although it is class 1 div 2, so a lot of this is more designed a little bit differently. You do have heat tracing in these cases. So again, it's all based on the same principles we've talked about today. We just have to look at some of the different. It's really now just becomes more of fitting the different technologies to the applications of you or your clients. Do you have a question here? Have you ever had cases where the addition of the reagent releases so much energy that a heat exchanger or upgrade in material construction is required? Yes, is the short answer. However, it's generally speaking, so acid and base reactions are actually very exothermic. You generally just don't see it in a standard wastewater treatment system because really your waste stream is not very strong. pH 2 waste or even pH 13.5 waste generally has a fairly marginal amount of actual really, by volume chemistry or really or molarity to cause any kind of significant temperature rise. When you do end up with, say, somebody putting, a couple of molar solution into your system, in addition to the standard waste streams, you can have some very exothermic reactions. We've actually at Burt Process designed a number of systems specifically designed to treat spent reagents. So if you have a 10 or 15%, say, acid that can go into a tank, be treated to neutral. And those systems always have built-in heat exchangers because you end up with a very exothermic case. I don't remember off the top of my head. I believe it's like 54 kilojoules per mole of reaction going off with those applications. So yes, when you get into more pure or low-grade reagents that you're now neutralizing in your treatment system, you definitely need to go to things like stainless steel or PVDF, and you definitely need to have a heat exchanger that can then remove that instantaneous heat of reaction. Otherwise, your chemistry can just boil. I've seen it happen before, particularly more in accidents where, say, somebody mixes an acid and a base together, that will just boil basically right in your face. So yes, that is something that does come up. Generally, if you do good system design up front, it shouldn't happen unknowingly unless somebody puts something incorrectly down the drain. But yes, pH reactions can actually be very exothermic. If anybody wants to watch a video of one of these systems in operation, we do have one here on our website that will actually show the complete operation of a PHX system. That and other videos are available on our website. And for those of you who don't know me, that's actually me in that picture I'm saying next to the PHX. My webcam was not functioning today, but will be up for future webinars. And speaking of future webinars, we do have a couple coming up. We have a chemical feed and polymer feed system webinar on June 5th of this year. And then we have a high purity water design one also scheduled for October 9th. If anyone is interested, those links are already up on the website. Thank you, and I'll be on here for a little while longer if you guys have any additional questions. Okay, we do have one question, which is, what are the pros and cons of using reagent drums versus reagent tanks as part of a system? So I did talk a little bit about reagents, and I showed some example pictures here where you did have reagent tanks sitting on a system, but it's not always the case. Some clients like to have just drums that they can bring in or bulk storage transfer directly into a pH system. It's really a question of chemical handling, and chemistry is a consumable of your system. So having onboard reagent tanks is nice. You can just kind of bring it in, put a wand or have a pump there and just fill your reagent vessel. Drums, you need to offload, you need to be able to put them on top of a spill pallet, you have to lift them, swap them out, pull the actual suction wand of the reagents out. So really no matter which way you do it, you still have to have some level of chemical exposure. So you're definitely going to want to wear things like face shields, gowned up, etc., for handling these. Personally, I'm more of a fan of reagent tanks, unless you're going to go more the bulk storage route. We generally only see that on very big systems, or if the client actually has client uses this in some other process, which I've seen that some industrial clients, they'll have, a 5,000 gallon bulk caustic tank on site, and they'll just take the waste stream out of there. We have one additional question here. What is the benefit of using carbon dioxide gas as an acid reagent? So carbon dioxide gas, I touched on this briefly during the presentation, but carbon dioxide gas can be used in place of a liquid acid, and it's good because it is very safe. If you do have carbon dioxide gas, and kind of a funny story here, I did a project at a power plant in Alaska, and apparently it's extremely expensive to ship acid to Alaska because nobody makes it up there. So everything there is basically done with CO2 gas, which I found was kind of interesting. CO2 gas is a little weaker than a liquid acid. It is essentially the acidic version of limestone. without getting too into the chemistry on that one. That is basically the opposite of what you think of as the passive media. CO2 gas, though, can be pumped at high flow rates, which then going into a mixer can then be dispersed, and you do change the tank a little bit. You definitely want to have a taller reagent, you definitely have a taller treatment tank to allow for better dissolving of your CO2 gas into your solution. Instead of using a chemical injection, you have a diffuser, which sits right under your mixer, which then allows for that to dissolve. The pH will move. If you have a very strong caustic, it will take a fair amount of CO2 gas to allow for to get good chemical treatment, but it is definitely a very viable option. Another question here, do you recommend heat tracing or altering your reagent chems if a system is located in an area where the temperature can go below 55 degrees? I would change the chemistry as opposed to heat tracing, personally. I generally don't even really recommend 50% caustic anymore, and I've seen it turn to jelly way too many times, and I would generally just use 25%. 25% caustic actually freezes at a temperature lower than water. So if you do have an area, say in like maybe a little less unconditioned mechanical space, that's probably where you see that typically up north, you may see the reagent, and you may see a 35 or 40 degree environment. I would probably go with just a lower grade reagent, certainly a lot more economical than heat tracing your entire chemical lines. If you have a problem where you need more caustic in your system, as opposed to utilizing using a stronger reagent, you could put in a high flow, low flow metering pump configuration, whereby when you have that stronger chemistry, you could inject at a higher flow rate, and then as your waste begins to get treated, you can drop down to a lower flow metering pump, which then gives you more control over your pH range. We have another question here. How common is solids precipitation due to pH reagent addition? How can it be handled? It depends. If you are treating a straight up, caustic reagent with an acid reagent, you will get some precipitation of salts in your system. You may also have the issue, and whoever sent this question, I probably would want to talk to you maybe a little bit more offline about this one, because there's a lot of kind of answers to this question. You may have a metals in your waste stream which are then oxidizing out, which would have to be removed because it could be a hazardous waste stream. If you're talking about just basic salt formation, you're probably going to end up with more like a sodium sulfate or something like that falling out in your solution. And that generally can be dumped down the drain. It's not particularly good. It'll probably pass through a bit of a filtration device. You may want to decant that off your treatment system, depending on how it's configured. But it's not a very common occurrence unless you have, A, two very strong reagents reacting, or B, you have something else in your system which is then precipitating, and then that would need to be handled a little bit differently. That precipitant may then be considered a hazardous waste byproduct, like a metal, or it could be like a fluoride precipitation or something like that. One last question here. What is the lifespan of these systems? Generally speaking, a pH system has a lifespan of about 20 years, give or take. That's generally based on the lifespan of the thermoplastic material of the tanks. Things like pH probes, they generally last about a year or so. You generally want to calibrate them. I'm going to talk about maintenance here for a second. I haven't really touched on that yet. pH probes and chemical reagents are definitely the maintenance and consumables of these systems. pH probes generally should be calibrated at least every quarter, preferably every month. If you have a very strong waste stream or something a little unusual like solids that could coat on your probe, you may have to clean them or calibrate them even more frequently than that. But generally speaking, a pH system will last about 20 years or so. One more question. Is it possible to get a copy of today's presentation and recording? Yes, I believe we are sending out a copy of these to everyone who sat through me for the past hour to listen. Again, if you guys have any more questions, you guys can feel free to reach out to me directly. My contact information is there, both my phone and email. And I want to thank everybody for attending today, and look forward to hopefully seeing you guys again in June. Thank you very much.